Okay, so let's start with precipitation. Before I even show you a slide, since we've talked about it so much, someone by raising hand remind us, what is a precipitation reaction? What do we see? What happens? What does it look like? Yeah, Connor.
You mix two ionic compounds, and then one of them could, or two of the ions mix together, and then they precipitate as a solid out of the liquid.
Good. So key components are we have aqueous substances, so ions floating around. Two of those ions link together, become a solid, and then we can see that, right? So in the lab, what was it that you were looking for to know if a precipitant formed? Color change or cloudiness, right? Okay, so precipitation reactions, once again, that insoluble product is formed from original things that are just aqueous. This rule right here was in your notes before, but just reminding you, this is the one solubility rule you have to have memorized. The other big table of solubility rules you don't have to have memorized. But this is one the AP test says you need to know that all sodiums, potassium, ammoniums, and nitrates are always soluble, meaning they're always aqueous. Okay? Okay, you have 2 minutes to look through your pink reactions and pull out any reaction you believe is a precipitation reaction. Ready, set, go.
This one. Oh, I didn't see that one.
Don't look at your orange one. That would be very confusing. So pull that out, put it to the side so I can see kind of what you're sorting. Yeah, so we're doing precipitation reaction. They blamed my scissors, but. All right, you got 15 more seconds. Yes, these are all. No, because you get negative points for the ones that don't belong. Okay, everybody good? Okay, between you and your buddy, I want you to hold up in the air the reactions and try to hold them so I can kind of see the reactions you believe are precipitations. So hold them up in the air. Some people are holding up 1, some are holding up 2, some are holding up 5, 4. We've got lots of thoughts here. Okay, here are the correct answers. So first off, with precipitation, you're looking for a solid as a product. What are you looking for on the reactant side? Aqueous. So, this reaction right here, so the copper bromide, sodium hydroxide, that would be one. So if you pick this one out, dang it. I guess they can't see me anyways. Wait, what am I doing? That was really confusing. Is it a problem if my timer's upside down?
No.
Does that mean it's going to be filming upside down?
Yeah, it is filming upside
So
down.
I'll have to flip it on my when I edit it? Do I have to flip it when I edit it?
What you need to do, yeah.
Well, no, I knew that. I just didn't know. Not totally confused. I just didn't know if it would fix itself, you know.
It's fixed now.
Okay. Okay. Second one that is also a precipitation reaction is the one that has Pb2 plus and CrO4 minus. Now, these look kind of different. What is the difference between them?
One of them has an aqueous solution.
So one has an aqueous solution on the end. Good. What else is different? Josh?
One of them's just like the net.
Yeah. So in a sense, this is the net. The one with the aqueous one, we've taken out the spectators. But they're still both. Does everyone see how it's still both precipitation? Okay. So that means this one with Ca2 plus and SO4 minus is also precipitation. So there's 3 precipitation reactions. So it's one smiley face for getting all three. Okay, questions though on why these are, and if you identified another one, why it's not. Everyone feels like, okay, I now know, if I got it wrong though, you now know what to do so you don't get it wrong again. That's always the key, right? Yeah,
so
Sam.
there's this one NH3 plus H2O. Like, are those both aqueous? Or is there no way of knowing unless it's written?
That's a good observation, Sam. First off, if it doesn't specify their states, it's not going to be precipitation. Because precipitation has to signify that something is becoming a solid. So if there's a reaction and they don't give you their states, then you know, at least you can't claim without more evidence if it is precipitation or not. So, good observation though. Any other questions on precipitation? Okay, next type of reaction. Okay, is known as an acid-base reaction. Now the pattern for an acid-base reaction is what we say it involves the transfer of a proton. Now it's kind of a weird terminology that chemists call it as a proton, but the idea is this. When we say protons with acids and bases, we're really referring to an H+. So look at the periodic table, everybody, find hydrogen. How many protons does hydrogen have? One. How many electrons does it have? One. So when hydrogen gives up its only electron, they kind of say it's just a proton. Now technically there's neutrons in there as well. But with acids, it's all about movement of H's. So hydrogen is key in an acid-base reaction. Something gives up the hydrogen and something takes it. By definition, so what's happening here, so here's this chemical. This is pulling the hydrogen off. See how it's attached over here? So the hydrogen moved. So the thing that accepts the proton is known as the base. So bases are known as proton acceptors. And acids are known as proton donors. And you always have both, that's why it's called acid-base reactions. Okay, take a minute and a half and look through your remaining pink equations and see if you can identify our acid bases. Ready, set, go.
You have 3 over here and 2 over here, and then you have 4 over here and 1 over here.
So once again, hydrogen is key, and then that hydrogen is moving from something to something else. No, good question though. Yeah, so the precipitation ones keep separate. It's not going to be one of those three. All right, got 15 more seconds. Okay, hold up in the air for me which reactions you think are acid-base reactions. So for this category, you can have a smiley face for every one that you found. It's not if they're... No, but if you get a wrong one, it subtracts a right one. Otherwise, then you can just... I think I'm good. Okay, so check with me. So there are 3 total. It looks like most of you found 2 of them, which is good. Okay. So, yeah, so this one right here, so, well, not the first one, but one of them, so there's one with calcium hydroxide, and then HNO2. So that is an acid-base reaction. Okay. Notice the look here. What else could this be classified as, though? It's also a double replacement. So these categories can overlap with our new categories. Technically, all precipitation reactions are double replacements, right? So there can be some overlap between the old ones we've learned and these new ones.
But it's not transferring H ions. It's just it's transferring the OH as a pair.
It depends on the direction you're looking at it, right? So the idea in this one is, and we'll talk more about acids and bases on Monday and identifying them. So everyone see how the H is with NO3, right? And then on the other side, it's not with the NO3. So the HNO3 is donating its H. It's then pairing up with something else, the OH, and becoming water. It's not a guarantee, but the production of water is also a key to a lot of acid-base reactions. Some don't make water, but a lot do, because that's the idea of them neutralizing each other, is the production of water. So kind of as a little side note, if you see that water is made, it could mean it's an acid-base reaction, okay? All right, another one that's acid-base is the NH3 plus H2O. So in this one, which one is losing its H? Good, so in this case, and we'll talk once again more about this, but water in this example can act as an acid. It's not a good acid, that's why it's okay for us to drink, like it's really, really weak. So water can behave like an acid, okay? And then the third one is the one where it has HCl plus H2O. And then in this case, water is actually now acting as a base because it's accepting the H from the HCl. Questions on identifying an acid-base reaction? Okay, now you should have 3 more by default left. Those 3 types of reactions are known as redox reactions. Redox reactions take the longest to truly identify. So if you have to separate between different things, I would always do precipitation first, because that's typically the easier ones. Then acid bases, and anything left in this unit is redox. I wouldn't try to find the redox ones first, because their pattern isn't as obvious by looking at them. Now looking at them though, what do you notice about 2 of them? How else could 2 of them be classified?
Single replacement.
So there's one that's single replacement, and the other ones are synthesis. Yeah. So most synthesis reactions and single replacement reactions are redox. Now there's more redox than just those, but if you see a synthesis, it can also help indicate it. So what a redox reaction is it's the transfer of electrons. So redox stands for reduction and oxidation. Redox is just like the nickname for it, shortcut. Okay, so it's about tracking where the electrons are moving. Now the 2 key vocab words of today are the word oxidized and reduced. When a substance is oxidized, it means that it has lost electrons. Reduction means that it has gained electrons. Now pause for 1 second. Why would scientists choose the word reduction for something that's being gained? Andrew?
Because electrons are negative, it gives it a more negative charge.
Very good. But this is where you gotta be careful because it's so easy sometimes to flip these definitions and then all your answers are backwards. Okay, so there are 2 little silly ways you can remember it if you like those types of things. So if you remember the word oil rig, and I used to write that on top of my test just because on tests it's easy to flip things right. So oxidation is losing, reduction is gaining. That's what it stands for. Oil rig. Or if you want, there's just 2 different ones. Or Leo says GR. Losing electrons is oxidizing, gaining electrons is reducing. So whichever one you like better. Depends on what school you go to. I learned this. Another teacher learned that, so she taught it to me. But okay, now looking at our picture here, in this synthesis reaction, we see lithium has 1 valence electron, fluorine has 7. When they bond, lithium gives its electron away. So we would say that lithium is being oxidized and fluorine is being reduced. Just like with acids and bases, you have to have both. You're never just going to have just oxidation. Because if something's losing electrons, something else has to gain electrons. Okay? All right, so let's take a look at a problem and a demo to see oxidation and reduction in life. So my top equation here, I have some solid copper. Okay, so here's my solid copper wire. Let's cut us a piece. Okay, I'm going to react it with aqueous silver nitrate. What does it mean when something's aqueous? Good, so silver nitrate is a solid, but I've dissolved it in water. And how are these things existing? Good, as separate ions, right? Okay, so, oh, I need a beaker. I know, the silver nitrate's holding my phone, so we'll have to move that for a second. Okay, turn to your table, buddy, and tell them your favorite Christmas song while I grab a beaker. Are you done?
Yeah.
Okay. Okay, so these need to be, because they turn in like multiple papers at the same time, but I want them sorted separately. So they're already alphabetized, so just keep them alphabetized, but then sort them out. Does that make sense?
That's like a one day.
Okay, now this isn't a super fast reaction, everybody. So we'll start it and then we'll kind of actually watch it through most of the class. And kind of see it progress. Okay, so here's my silver nitrate. Looks like water because they're dissolved. Okay, I'm going to drop my, where'd my wire go? I'm not going to drink it because it's highly poisonous. No, silver nitrate. I mean, you probably shouldn't eat copper. You can get copper poisoning too, but. Okay, so I'm dropping the wire in. Okay, and then you'll start to see a small change, and then it'll change more.
Black.
Yeah, so does everyone see kind of the shine of our copper starting to fade a little bit? No?
Is it gonna turn Statue of Liberty color?
Yeah, Statue of Liberty color. That's my favorite color.
I love Statue of Liberty colors.
Okay, so you can taste it right now.
See what the breakfast eating Statue of Liberty.
Okay, now look at our equation, everybody. So this is the overall. This reaction, what have I removed?
It's proton.
Electrons.
What's different? Look at this one. Look at this one. The font did change. That wasn't on purpose, but. What's changed from the top reaction to the second reaction? Nitrate. Okay, So we just removed the spectator. Okay, so this reaction right here is the net ionic equation. So even with redox, you can have net ionic equations. Net ionic just means to remove things that aren't doing anything. Okay, so right now, I'll hold it up because it's even darker. Okay, there's something forming on the outside of my copper. What is it? What does my reaction say I'm making?
Copper nitrate.
Close. Wrong symbol. Silver. So in this beaker right now, before your very eyes, we are making solid silver. Okay?
So is the Statue of Liberty covered in silver?
If you dunked it in silver nitrate, it would. Okay, so what will happen, everyone? The silver will continue to form, and it's forming as like crystals or flakes. Okay, so in a second, after it grows a little bit, I'll swirl it so the silver can fall off, so we can expose the copper so it can keep reacting. And then we'll just keep making silver and watch it as we go through class. Okay, now this right here, in a net reaction, or even not in a net, we can track the movement of the electrons to identify what's being oxidized and what's being reduced. So I see here that solid copper, when something is all by itself, it doesn't have a charge. It's just an element. It's changing to an ion with a +2 charge. If something gets more positive, is it gaining or losing electrons? Losing. And losing means oxidation. So in this reaction, our copper is being oxidized. Our silver is going from +1 to 0. And so our silver is being reduced. So we're now going to change this overall net and split it into 2 half reactions. For the oxidation reaction, we're going to write what's happening with copper. So copper is going from solid copper to copper 2+. If it's going from 0 to +2, how many electrons is it losing? 2. So in a half reaction, you add to show where the electrons are and how many it's changing. Okay? For the reduction one, we have silver ions changing into solid silver. Oops. And where do the electrons belong in this reaction? Are they being lost or gained? Gained. So now we're going to put them on the left. I should have left a little bit more space. Now, how many electrons are being gained?
1.
How is it 2 if we're going from +1 to 0?
Because there's 2.
No, you were right, Macy. It is 2.
Which is
Because there's 2 silver atoms. Now, this is key to oxidation and reduction. The number of electrons lost has to equal the number of electrons gained. Unless you're some magician who can just make electrons appear, it doesn't work, right? They have to balance out, okay? All right, next smiley face question. With your table, buddy, you're going to do these 2 things for me. With this new equation, you're going to label which one is being oxidized and which one's being reduced. So step 1, tell me what's being oxidized and what's being reduced. So label the reactions. Step 2 is you're going to do the reverse of what we just did. So we had an overall that we broke into 2. I'm giving you 2. I want you to combine it into 1.
not a net equation, just the entire equation.
It can be net. Okay, ready, go. So what's being oxidized, what's being reduced, and then combine them 6 overall. Now you're with a buddy for a reason, so talk to your buddy. Oh, in case you don't know, turn to your buddy and say, hello, my name is, in case you're going to do this. Make sure you know your buddy's name.
So, so it's still like we're just combining there. So the electrons being supplied by the AL, or no, the AL.
Yes, good catch.
There's 3 electron ions. The 2 electrons being supplied by our.
Remember, the number of electrons lost has to equal the number of electrons gained in the overall reaction.
So it should be 2 aluminum and 3 zinc.
You're almost there. You're over me. It's not like you're not combining. Look at the one above compared to the one below. You're doing more work than you need to.
So that means we're over.
No, it's wrong. You're doing more work and it's not getting you in the right direction. The number of electrons lost has to equal the number of electrons gained.
So you need 2 AL, right?
Yeah, I think
So that's
Look at your the rest of your seats.
okay.
Yes, good work, guys.
Oh yeah.
It all has to be balanced.
There we go.
Now the equation is balanced. You have 2 AL on that side, 1 AL on that side. There you go. That looks better. Okay, you got 15 more seconds. Then we'll check it on the board for some smileys. Okay, everyone, eyes up here. So when you're going in the other direction and writing an overall reaction, once again, the number of electrons lost has to equal the number of electrons gained. In this reaction, so first off, you can have a smiley face if you labeled this one as oxidation and this one as reduction. So 2 smiley faces there. Okay? But then, this one is losing 3 and this one is gaining 2. They have to balance out, so you have to times them. The way I think about it is you have to multiply them so you get to the least common multiple of them both. So since 1, 3, and 1 is 2, I got to get them both to 6. So I'm going to times this reaction by 2 and this reaction by 3, and then I can combine them. So we're going to have 2 aluminums plus 3 zinc ions, changing into 2 aluminum ions and 3 zinc atoms. If you have that, you can have a third smiley face. Questions on combining halves into a whole? Yeah, Sam.
If you're losing the electron, why don't you put it? Oh, never mind. Like, why don't you put it right?
A subtraction sign? No, that's a good question. So in chemistry, we don't use subtraction signs because it's about what side of the equation it's on, right? By being on the right, that's the way to show, hey, this is being lost. And to be on the left shows, hey, this is being gained. Does that make sense? Okay. Okay, so the last thing that we need to learn is, so in these reactions, it's easy to see what's being oxidized and what's being reduced. In other chemical reactions, it's not so easy. And so rather than having to count all the electrons and stuff and see where they're going, scientists have come up with a bookkeeping way to track it, known as oxidation states. Now keep in mind, these oxidation states don't represent a whole lot besides tracking the movement of electrons. So we're going to learn a series of rules for oxidation states and then use that to help us identify oxidation and reduction. Okay, first off though, our silver's looking really good, so we need to bring this around.
Whoa, that looks sick.
Oh,
See our little fuzzy caterpillar in there. So that is literally silver metal, everybody. Silver's not worth as much as people.
That's why it was used as utensils. If we can make it, it's also.
Yeah, so keep in mind, don't be deceived like me Mushy kids when I do this and oh my gosh, you made silver. Did I really make silver?
No.
I pulled it out of something I already had, right? Now, you can guess how expensive you think silver nitrate is. It's way expensive. Like, I think that bottle was like 90. No, it's silver nitrate. Well, so it's like a powder. So when I do this, yeah, I just made it fire. So what I'm going to do, everybody, is I'm going to stir it. Okay, watch this. So the silver's going to fall off because it's just, there's specks, right? Flaky. So I'm going to knock it around.
Why it's so much thinner? Because it was.
Yeah, so the wire's going to get thinner because where's the copper going? It's into the solution. So I'll let it sit and we'll grow more silver.
Wait, does that mean the solution's gonna dry?
That's such a weird thing to say.
You should put it in.
Let's grow.
Say it again, Josh.
Does that mean the solution's gonna dry?
Hey, you should.
Yep. Yep. So this is last period, so it's been going a long time. So the solution turns blue as the copper goes into it. So
I can see a little tint of blue in ours.
I think ours is starting to get there. So
I can see a little. Not as much as.
okay. Let's talk about the rules and then we'll apply the rules. Okay, so here are the rules for assigning oxidation states. If something has a designated rule, meaning it's always one way, then you go off the always rules first. For example, group 1 metals. So when I use the word group in terms of the periodic table, what am I referring to? The column, right? So hydrogen's column is group 1. Okay, but it's group 1 metal, so hydrogen's not part of that rule because it's not a metal. Okay, but those are always plus 1. Okay, group 2 metals are always plus 2. Fluorine is always minus 1. So it's kind of a weird thing, but you're going to start with the rules that are always. Do those first. Then you go to the usual rules and use those next because they are mostly this way, but they can sometimes vary. Oxygen is usually minus 2, but in some cases it can be different. Okay? Other usual rules is hydrogen is usually plus 1, except in metal hydrides where it's negative 1. So what that means, if you want to interpret this exception, is when hydrogen is with something that is more electronegative than itself, it's going to be a negative 1. Okay, and I'll show you an example of where that fits in. Okay, and then chlorine is usually minus 1. Besides these, to find out all the other oxidation states, we use algebra. Okay, it's really simple algebra, like 6th grade stuff here. Okay, so the two things with it are compounds have to add up to 0 or their charge. So if they have a charge, they add up to the charge. If they don't have a charge, then they add up to 0. If something doesn't have a charge and it's all by itself, then its oxidation state is just 0. Okay? All right, let's apply the rules. Okay? All right, so what we want to do here is determine the oxidation state for sulfur in each of these compounds. So let's start with A right here. So sulfur's with hydrogen. What was the rule for hydrogen? Good, so it's usually +1. Unless what it's with is less electronegative, but since sulfur is so far, it's more, so yes, it's a +1. Okay? Now, to determine sulfurs, because we don't have a rule for sulfur, we know that as a whole, it has to add up to 0. So there's 2 hydrogens, so it's -2. Notice that you write the individual oxidation number, not the total of all the hydrogens. Okay, because if a question said, what is the oxidation state for hydrogen, the answer is +1. It's not +2. So it's done by individual atoms. Okay, B. We have sulfur all by itself with nothing else. So it's 0. Did you have a question, Sam?
Yeah, so did we just get lucky that sulfur matches up with its...
In that case, yes.
Okay.
But that's a great observation of showing oxidation states are not their charge because it can vary. So, okay, coming to this one. What's the rule for chlorine? Usually -1. So we don't have anything else to believe, so we go off the usual rule. I have 2 of them. So sulfur in this case must be a +2. Okay, moving on. Coming here. Which ones do I have rules for? So oxygen.
Nitrogen.
And we do have one for sodium.
That's what I meant to say.
So sodium's rule is +1 because it's in group 1. Oxygen's rule is usually -2. Now, if it helps to not do it in your head, you can total them up underneath. So I have 2 sodium, so total that's +2. I have 4 oxygen, so total that's -8. What does it have to all add up to? 0. So sulfur would be +6. Everyone see that? Now, if a question were to say, what is the oxidation state for oxygen? The answer is -2. The total is not the oxidation state. We just use that to get the others. Okay, last one here. So oxidation for oxygen is -2 again. I have 4 of them. So -8. What does it need to add up to this time though? So it needs to add up to -2, not 0. So it's also +6 again. Questions before you try it on your own for some smileys?
Are there any smileys going to be per question?
Per question. Okay, so 5 questions. Ready, set, go. Talk to your table buddy, figure them out.
Peroxide breaks. So up here, peroxide is
Are we doing the rest of this? I don't
Do you want to put it in the lab? Just go in it.
Why'd you write them up?
Okay, anyone need another second? Feel good? Okay. Okay, check them as we go. Ask questions if you need. This is what 4.9, the homework that you're going to get tonight, is going to have you do more of. Okay, so in this one, fluorine is -1. I have 3 of them, so that means manganese must be 3+. Good. Okay, oxygen is -2. I have 2 of them, so that means manganese would be +4.
Wait.
Stop me if you have a question. Yeah.
It says on the thing that peroxides break the rule. I don't know. Is that?
Do you know how? Like, are you asking how do I know it's a peroxide?
Yeah.
Or you thought that was a
I thought
peroxide?
that was a peroxide. What do you do?
So peroxide is when oxygen is 2 to minus.
Okay.
So you would have there would have been another 2 over there. I'll try to show you an example in a second of a peroxide so you know the difference. But good question, Connor. Okay, come in here. Potassium is +1. I have 3 of them. Oxygen is -2. I have 4 of them. I need it to add up to 0, so +5. Is that right? Questions? Okay, coming over here, +1 -2. That would be -8, so 7. And 0. Give yourself a smiley face for each one you got right. Questions on oxidation states? Yeah, Hannah. Less. Because in general, whichever one has the highest electronegativity will always have the most negative number. So, thanks, Connor. Okay, do you want to take some of these and start looking through them? So I made a key off this one. So you don't check anything on the front because I already checked that. Pretty much just make sure that you have that there, but we'll check the data later. So that's 4 points. And then 3.3 comes this table in. Just glance through. They could pick whatever card they wanted, but they just needed a net ionic equilibrium, so make sure they're net with other spectators. 1 point each. Her answers are pretty good, but I trust you also know what they're asking. Just 1 point for everything. They did need to justify why they picked B. So if they didn't, they don't get that point. And then on the tables, so kind of 5 points per table maybe. But then what you're looking for is anywhere where there was a precipitant, they should have something highlighted or circled. So if they don't have any of them, it's 5. So I think that adds up to 30. Okay. Now, the point of learning oxidation states is to track what's being oxidized and what's being reduced when it's not as clear. Once again, in our silver, oh look, we made another caterpillar.
Check it out.
Oh, that didn't work.
It's so satisfying.
Watching it just come off. And can you see the water starting to tint a little bit?
I can see there's still copper underneath that layer that came off. So is that also just gonna start reacting?
Yeah, it all kind of depends on limiting reactants, right? Once I run out of silver, then it will stop. But if I have enough silver in there, then yep, it'll just keep going until all the copper is gone.
We should put that on the camera because we can't see it.
Here you go, Davin and Creed. Thank you. It's true, that's a good point. Yeah, when it grows again. It doesn't look pretty right now. Okay, so in a reaction, let's do the top one together and then we'll do the bottom one for some more smiley faces. We're going to write oxidation numbers to see what's being oxidized and what's being reduced. Okay? All right, so going through our list here, Which one do I have a rule for? Hydrogen. Now hydrogen is +1 or it could be -1. This is a case where it's a -1. Carbon has a lower electronegativity compared to hydrogen. A hint that can kind of help is if hydrogen is listed second, it's going to be negative because it kind of shows the bonding behavior a little bit, so that might help if you're unsure. But yeah, Eli.
If there's anything after the hydrogen, would that just be +1?
Yeah, but hydrogen's really never too much in the middle. But yeah, if it was, then I'd say go on the +1 side. So, okay, so then I have 4 hydrogens, so total, that's -4. So that means my carbon needs to add up to +4, but I have 2 carbons, so carbon's oxidation number is +2. Everyone see how we did that one? Okay, good? Okay, come in here, what's oxidation number? 0, it's all by itself. Right, when something is by itself, doesn't matter diatomic or more. If it's not with something different, it's just 0. All right, coming to CO2, oxygen is -2. There's 2 of them, so then it's going to be +4. Okay, come in here, -2. Hydrogen would be +1. Questions on any of those numbers? Now, let's track numbers that change. Okay? So on this side, oxygen is 0. On this side, it's going to -2, right? So it's going -2 in 2 different spots. What does that mean about my oxygen if it's getting more negative? So good. So oxygen is being reduced. Okay? Now, hydrogen is going from, now notice when you track oxidation states, track the individual, not the totals. So hydrogen is going from -1 to +1. So what's happening to hydrogen? Good, it's being oxidized. Carbon is going from +2 to +4, so what's happening to it? Also being oxidized. Now notice that the amount of oxidation has to equal the amount of reduction. So we have 2 things being oxidized, and it's one thing, but notice it's 2 processes, 2 reductions. Questions? Yeah, Macy.
When you write the oxidation equation thing, would you combine them all together, or would you just use separate ones?
So like the half thing you mean?
Yeah.
Well, so for ones that look like this, we will actually take them to half reactions too. But we're going to learn that later on. For now, the only ones you have to split into half ones are the ones that look like the copper one, where it's just like clear of how to split it. Because this one gets tricky because this is going like in 2 places and stuff like that. So good question though.
How do they name oxidation? Oxidization, I still didn't pronounce that right, and reduction. How do they come up with this?
Well, my thought of as far as I know, I've never researched it, but reduction is based on the fact that when you gain electrons, your charge becomes more negative, and reduce means to get more negative or to go down. Oxidation, as far as I understand, there's a fact of how when things are exposed to oxygen, rusting is oxidation. But you can have oxidation without oxygen, right? We have it in there right now. So I think that's where it came from. But okay, try this one with your table buddy. Ready, set, go. all by itself. It has a charge. When they do that, when they charge, they add up to 2. It's only one thing. Yeah, they're alone, but they it's okay. But we could just do that and labs can be wrong because they have that high risk. So I guess, yeah, it doesn't have to match up
I found this it was minus
It might have changed.
So when it's not changing,
Because they're not changing, right? So they're part of it, and since they could be kind of like spectators, because they're not actually. You don't do anything with them. Good question. Okay, if you're not done, don't look up here. If you're done, check it with me. Okay, questions? Yeah, Eli. Yep, it's kind of that idea of they either have to add up to 0 or to their charge. So if they have a charge, then it is just the charge. Yeah, Calvin.
So I have questions like, how do I tell that it's
So it's all about the change, right? So when the number goes more positive, it means it's giving up electrons. Because electrons are negative, right? So if you give away a negative, you'll become more positive. So an increase, here's kind of like a summary, an increase in number, like oxidation state, means it's been oxidized. A decrease in oxidation state means it's being reduced. Does that answer your question, Calvin?
Yeah.
Okay. Other questions? Our equation disappeared. Now, what does it mean about those other ones that just didn't change? Yeah, they're there. They're maybe like kind of like spectators, right? But you don't connect lines between them or anything because they're just not changing. So, now tell me this, problem solve. What if you did a problem and you had two things being reduced, but nothing being oxidized? You have done something wrong because you have to be balanced, right? The electrons lost have to equal the electrons gained. So if you get two reductions on the homework or two oxidations, check something because something's off.
Wait, could you get like 3 reductions, but like one big oxidation?
Yeah, because we're not totally calculating electrons yet, possibly. Kind of like on our last one, how it kind of looked like. But I would say for the most part, just it should always be 1 and 1 of each. But good question. Any other questions on oxidation or reduction? Yeah, Eli.
Also on the homework, we have to write out like the equations, like
Like the half reactions. So the only half reaction types you're going to have to do. Sorry, I was trying to get this to come back alive here. Oh, there you go. Are like the ones we did here. So like these ones, yes.
So it'll just be easy.
But in terms of like these guys, like changing this into half reactions, no.
Oh.
You just need to be able to identify, okay, this is being oxidized and this is being reduced. So, okay, I'll pass out your homework 4.9. The homework is listed there if you like to take a picture of it. You can put your pink slips back in the baggie for me. Oh yeah, so you can have 2 smiley faces if you have the oxidation reduction.
Oh, yes.
What time is the bathroom? You have time for you another smiley face question just so we have Okay, we got a few minutes left, so we'll do some smiley face questions just to end off. Oh, look, we got another caterpillar. Can they see that? Does that look like, is that on the screen? Yeah. Higher, lower?
Wait, maybe? Should I like put my flashlight on so they can see the shiny?
Oh, so they can see the sparkle. There's some really good long crystals growing off this one.
Let's look at this.
Look at that. Do you see? Look how long those ones are.
Whoa, that's cool. All full power.
That looks pretty good. Thank you. I'm sure that was a nice touch. Okay, I'm gonna write an overall. You have to split it into half reactions and which one's being oxidized and which one's being reduced. Find somewhere to write it down. What do we want to react with? All right, what's being oxidized, what's being reduced, and combine it into an overall.
Oh, this is a smiley face question.
Everything is important in math.